Let's take a look at example 13.7 from the text. It's going to involve normal, tangential, and binormal components. We have a platform, cylindrical platform, and it's allowed to rotate in this direction right here. As it's rotating, we have this puck with some mass, 3 kilograms, and we're going to gently set it on the surface and allow friction to cause it to accelerate and eventually match speeds. We're not interested when it matches speeds. We're interested when the speed is enough in this tension right here to break the cord if the T max in that cord is 100 newtons. So after 100 newtons it's going to break. When's that going to happen? And they give us the coefficient of friction as 0.1. Okay, the puck is also dropped at rest as a keyword, so we can start its initial velocity at 0. So one thing that might not be intuitive right away is that the motion of the platform and the frictional force are the same way. That's not the way to look at it necessarily, though. The disc does not want to move as the motion is rotating, so it's got almost like an inertial force kind of pointed in the opposite direction. We're not going to use those terms. You'll see some terms like that in future classes, but it doesn't want to move. The thing that is moving it is a frictional force in the unit tangent direction, and that frictional force is caused by the coefficient times the normal force. So go ahead and get one equation knocked out that we'll need later. Hold on to this for later. Okay, let's do a free body diagram. If I look at this puck, why always? If I look at this puck as it's traveling on its curved path, maybe it's right about here. I'm going to draw my coordinate system at the puck because of this coordinate system. That's how we do it. So this looks like it could be some tangent to the path pointing towards the center of the rotating disc would be our normal component, and making our binormal would be pointing straight up. Okay, let's add some forces on here. Well, we saw that we have this force of friction. That's our driving force that's causing the puck to accelerate. It's in the tangential direction and remains in the tangential direction. There's also a tension right here, and that tension will increase as the puck speeds up until it can take no more, and then it'll snap. What else do we have? We should have drawn it first. mg going down and the normal force going up. Alright, anything else? Don't think so. Alright, let's start Newton's second law. So let's sum some forces on that free body diagram. So if I sum the forces, and let's do the normal direction first, I get mass times the acceleration in the normal. This, what do we have in the normal direction? It looks like I just have a tension. And that is going to equal the mass, which is 3. And then if we remember that the normal component is equal to the speed squared over the radius, we can go ahead and plug that in. Alright, simplifying with rho equal to 1 meter, I get tension equal to 3v squared. So it is a function of velocity. We can now say, well, T max is equal to 100 newtons. So let's put 100 newtons here. and we can find out what velocity right away. 5.77 meters per second is its speed as it travels. At which the cord snaps or breaks. Okay, let's go ahead and see what we can get from another direction. Let's sum the forces in the tangential direction. That would equal the mass times the acceleration in the tangent direction. Alright, well, in the tangential direction I just have this frictional force right here. So we saw that that frictional force could be written as 0.1 times the normal force. And that's the only force we have, so that's going to equal the mass, 3 kilograms, times the acceleration in the tangent direction. Alright, let's hold on to that equation, and let's sum the forces in the binormal direction. It's going to equal 0. So in the binormal direction, I just have a positive normal force and a negative weight. So normal force minus mg is equal to 0. This is where the binormal component usually comes in handy. We can typically just use it to find what the weight of an object is, or the normal force, and we can find that the normal force in this case is 29.43 newtons by moving that over here. Alright, I'm going to take this equation. We know the normal force now, so I can say the acceleration is equal to 0.1 over 3 times the normal force if I rearrange. And that gives me a tangential component of acceleration to be 0.981 meters per second squared. Alright, now we have the speed at which it occurs, we have the tangential component of acceleration. We can use kinematics. Let's use V final is equal to V initial or V naught plus that constant acceleration times time. Because this is just a number, it's a constant value. And the frictional force is only a function of the normal force, not the speed the disk is spinning at. So even though if it's slipping, the frictional force is the same regardless of how fast it's slipping. Try to wrap your head around that. So we went from rest, so this goes to 0, and I get a V final. Take this acceleration right here, 0.981, and we want to know how long it takes for that to happen. We get T is equal to 5.89 seconds. Pretty interesting problem. Kind of used just about everything we learned. A little bit of everything.